In this video, we're going to prove a lot of facts about vectors in Rn. If u, v, and w are vectors in Rn, and c and d are any real scalars, then u plus v is in R. That means closure. Vector addition is commutative. Vector addition is associative. There exists what's called the zero vector in Rn such that u times 0 or u plus 0 or 0 plus u equals u. And for every u in Rn, there exists their inverse of u, called negative u, such that when you add those two together, you get the zero vector. C times u, a scalar times vector u, is a vector in Rn. So that means Rn is closed under scalar multiplication. If you have the sum of two vectors and you multiply that result by a scalar, you can distribute the scalar. If you have a sum of scalars times u, you can distribute the scalars. If you have c times du, you can collect the scalars and multiply it by u. And lastly, 1 times u is just u. Now, let's see if we can do this. And in alpha, it should say x to the n. Maybe I will do this right here. So let u equal u1, u2 up to un plus v, which is v1 plus v2 up to vn. And u1 through un and v1 through vn, they are real numbers. And when you add them component-wise. You add the first components, the second components, all the way down to the last component. Now, when you add these two real numbers, you get a real number. You add those two real numbers, you get a single real number. You add those real numbers, you get a real number. Well, that's n real numbers. That's in Rn. So we actually have, let me get rid of these check marks. So the alpha is checked. We proved it. Now I'm going to go right to A. Since these are real numbers, I can switch them. And since u2 and v2 are real numbers, I'm allowed to switch them all the way down to un plus vn. When I switch that, I get vn plus un. Vn plus un. But it turns out that that's just v1 up to vn plus u1 all the way down to un. Well, that's v plus u. And over here, we had u plus v. So I proved A. I proved alpha and A. Now, the commutative law. I'll try to do that down here. I meant to say the associative law. So you have u plus v in brackets plus w. Well, we know where u plus v in brackets are. We just added them and that's what we got. we have u1 plus v1, u2 plus v2, all the way down to un plus vn. And that's u plus v, and I want to add w, which, take a guess, is w1, w2, all the way down to wn. Now, I add these. Right now, we're going to think of that as one number plus another number. Is u1 plus v1 plus w1, u2 plus v2 plus w2, all the way down to un plus vn plus wn. Now I'm going to think of them, each entry, as three numbers. And three real numbers have the associative law. This is 1 plus 2 plus 3 real numbers. It has the associative law. That this is the same as u1 plus v1 plus w1, and u2 plus v2 plus w2, all the way down to un plus vn plus wn. Now I'll think of that as just one entry. One entry plus another. One plus another. I can break them up. This is u1, u2, up to un, plus v1 plus w1, v2 plus w2, all the way down to vn plus wn. But this matrix, and I can put brackets around each of those. In fact, that's how they were bracketed. So this matrix, well, that vector is u, plus this vector is v plus w. And I just showed that this equals that. That gives me letter B. Okay, now letter C. Let's get some space going. Letter C. Now, if I take u, which is u1, u2, all the way up to un, and I add the vector, which is all zeros, and you should comment that this is an Rn, because I have to have 0 in Rn, and this becomes u1 plus 0, u2 plus 0, all the way down to un plus 0. But un plus 0, u1 plus 0 is u1, u2 plus 0 is u2. Remember, those are real numbers, and if you have a real number and you add 0, you just get back that real number, un. So this is u. So I took u, I added this vector, and I got back u. And so I showed that this is u. If I show it the other way, well, what I can say is I can invoke letter A right now. This here is the same as 0, 0, 0 plus u1, u2 up to un. And remember, we can only do that. We only prove that if that's true if u and v are in Rn. But this is in Rn and this is in Rn. And you better say that this, and I said it, this 0 vector is in Rn. So I showed it both ways. I showed this equals to u, and I showed that is equal to u. That is, this equals this, which equals this, which equals this, which equals u. Likewise, this equals this, which equals this, which equals u. Okay, now, and only now that we established that there is a zero vector, now we can talk about inverses. Letter D. If you have u, which is u1, u2, all the way up to un, and you add, now u1, u2, etc., they're real numbers. And if you put a minus sign in front of a real number, you get a real number. Here's a real number. I put a minus sign in front of it, I get -7. Here's a real number. I put a minus sign in front of it, I get a real number. These are real numbers. And since they're n real numbers, it's an Rn, you must state that. So this is equal to u1 plus negative u1, u2 plus negative u2, all the way down to un plus negative un. But those are all zeros. So here, given a vector u, I found this inverse. I found another vector to add to it to get to the zero vector. So I establish D. Now we go on to beta. And let's see what we have here. We have a scalar times u. u1, u2, up to un. Now remember, the u1 and the u2, all the way up to un, they're real numbers. And so is the number c. And a scalar multiplication means you multiply each of the n entries by the number c. And like I said, since c is a real number and ui is a real number, c times ui is a real number, where I is 1 or 2 or 3 up to n. So this is in Rn. It's n numbers. It's n real numbers. 1, 2, 3, 4, 5, 6, eventually n. Okay, so I established that scalar multiplication is closed. Okay, now C times u plus v. Well, it's c times u plus v. u1, u2, up to un, plus v, which is v1, v2, up to vn. This is c times u1 plus v1, u2, plus v2, all the way down to un plus vn. And each entry gets multiplied by c. So it's c times the first entry, which is u1, v1 plus v1. u1 plus v1, c times u2 plus v2, all the way down to c times un plus vn. But u, v, and c, they're real numbers. So we have, distributing the c, we have cu1 plus cv1, cu2 plus cv2, all the way down to cun plus cvn. But that's nothing more than cu1, cu2, all the way down to cun plus Yeah, CV1, CV2, all the way down to CVN. Okay, now, this here is nothing more than C times U1, U2, I factored out the scalar, plus this here is nothing more than C times V1, V2, down to Vn. And here's where I have it. That's U, vector U, C times U. C times U, it does say plus C times vector V. C times vector V. And I wanted to show that I can distribute the scalar. So letter E is done. Now letter F. You have C plus D times U. Well, this is C plus D. Think of C plus D as one scalar right now. You add two numbers like C and D, like 4 and 5, you get one number. Times vector U, U1, U2, up to UN. So, we get this one number times U1, this one number times U2, this one number times UN. Now I'll think about it as two numbers. C plus D is two numbers. So I distribute. I get CU1 plus DU1. I get CU2 plus DU2. All the way down to CUN plus DUN. But that's nothing more than CU1, CU2, all the way down to CUN plus D times U1, D times U2, all the way down to D times UN equals. From here I can factor out a C. I get C times U1 down to UN. Here I can factor out the D, and I get D times V1, V2, all the way down to Vn. So I have C times this, but that's vector U. I get C times vector U plus D times this vector. But this vector is V. So this is equal to that, which is exactly what letter F asked me to do. Okay, now we go on to letter G. Okay, these are very, very straightforward. We go on to letter G. C times du. Well, there's C. Well, what's du? Well, it's D, scalar D times U. U1, U2, up to UN. And this is C times whatever this is. Well, this scalar D tells me to multiply each entry in U by D. So I get this. Okay. Now, D times U1 is just a real number. D times U2 is a real number. D times UN is a real number. In fact, what's in this bracket is a vector in Rn. And I want C times it. Okay, so I get C times the first entry, C times the second entry, all the way down to C times the nth entry. But these are all just real numbers being multiplied. So the commutative law comes into effect. Sorry, associative law. Instead of multiplying C by du, I can multiply CD first and multiply that by U1. C and D first, then times U2. All the way down to CD first times UN. Now, think of CD as one number. After all, when you multiply two numbers, you get one number. Sometimes you want to think of a product as one number. Sometimes when it's favorable, you want to think of it as two numbers. Same with a sum. 3 plus 4. If you tell me this 3 plus 4 is two numbers, I don't have a problem with that. But you better tell me the two numbers it equals. Okay, and you can't tell me it equals 3 because 3 plus 4 is not 3. You can't tell me it equals 4 because 3 plus 4 is not 4. 3 plus 4 is one number. It is the number 7. There is no other number. Okay, so now I could factor out the scalar. Since U1, U2, all the way up to UN, they're all being multiplied by this one scalar, CD, I can factor it out. I get U1, U2, UN. So then I get CD times this, which is vector U. Got G. Now, I was really worried about how to prove letter H, but I'm no longer worried. In other type of problems, you have to be a bit clever. But 1 is a scalar. So this is 1 times U1, U2 up to UN. And then I have 1 times U1, 1 times U2 up to 1 times UN. And 1 has the property that when you multiply it by U1, you get the real number U1, you get U1. And when you take the real number 1 and multiply it by the real number U2, you get U2 all the way down to UN. But it turns out that this vector in Rn is vector U. So 1 times U equals U. And I did for look like 10 proofs in a few minutes. If you like proofs like this, subscribe to my channel. That's all I do. Nothing but proofs. Nothing but math proofs. Tell your friends about my channel. And as always, please watch and learn.